Today we are going to discuss lab number 5 of linear control system. Title of our lab is Mathematical Modeling of Physical System. In this lab we are going to discuss how we can derive a mathematical model from any physical system and how we can implement or solve that mathematical modeling by using MATLAB. So let's start with the example. We have we have here mass spring system model. You can see in figure 5.1. So here a mass is attached to a spring. We have applied force Fa of t. You can see in the right hand side direction. So there are two external forces will be act upon this mass, and these forces will be spring force and frictional force. As you can see, the direction of these forces are opposite because we are pulling mass in this direction, so spring and friction force will try to pull the mass in the other direction. So I hope the scenario of this figure is clear to you all. Now we have to derive its mathematical model and then solve it in the MATLAB. So here we have some quantities like acceleration. We can see there is a displacement. Whenever we applied a force on a mass, it will cover some distance in a particular direction because force is a vector quantity and its direction is shown by this arrowhead. So here x of t is the displacement. You can see over here as well. Velocity is equals to the rate of change of displacement. So I can write this v equals to first derivative, which is the rate of change of displacement, and acceleration is equals to the rate of change of velocity. So if we would like to convert this acceleration into the displacement form, so we have to take its double derivative. So velocity equals to the first derivative of displacement and acceleration will equal to the second derivative of displacement, because acceleration is by definition is equals to the rate of change of velocity. So I hope this supposition is clear to you all, or these values are clear to you all. So here we have equation 5.1, which is a law of physics. Like if we applied any force, so it will be equal to the sum of individual forces act upon that body. So we have three different forces in this case. The first one is the mass multiplied by acceleration, the second is the frictional force, and third is the spring force. So in this case, for frictional force, we know that it will be equal to the frictional coefficient multiplied by the velocity. We know the value of velocity because we want to convert each quantity into the displacement. So we have to put the values in the form of displacement. So b multiplied by v equals to dx over dt. Here we have b as well. Then we have spring force. Spring force will be equal to the spring constant multiplied by the displacement. Now we are going to put these values in equation 5.1. You can see mass constant equals to the m, and acceleration is equals to the d, second derivative of displacement we have supposed here. Then we have frictional force, so it will be equal to the b. From this equation, b multiplied by v, and v equals to the dx over dt. And the last quantity we have the spring constant or spring force, which is equals to the spring constant multiplied by the displacement covered. So here here you can see we have developed a relationship between applied force and the displacement x of t. This equation, you can see it's a linear relationship between these two quantities, but in real scenario these relationship will be more complicated and can be linear. So if they are and can be non-linear. So if they are non-linear, then we have a quantity y as x raised to power, which shows that the spring force or the frictional force can be a non-linear quantity, and it will depend on the value of y. If we would like to observe the results in the graphical format or non-linear relationship, so these quantities will depend on the value of y. As y changes, the response will also gets changed. So to identify whether the equation or the system is linear or non-linear, we have already discussed the properties homogeneity and superposition. We have to satisfy these two properties if the system is to be a linear. So this is a non-linear relationship. Now, solving these differential equation on MATLAB, our focus is to solve these equation by using a MATLAB tool. So here we are using we are discussing two different examples. First, we have a speed cruise control example. Here you can see that from the same equation, from the same above equation, we have discussed or derived equation number 5.2, this one. This equation, here we have supposed the spring force F of S equals to 0. So by substituting F of S equals to 0, we will left with the two quantities. So here we have MA force and frictional force is equal to the total applied force. Now we are going to solve this equation by using MATLAB code. So we have to find out the relationship of velocity with the applied force. So we have converted the displacement into the velocity format. So second derivative of displacement equals to the first derivative of velocity. You can see in equation 5.5, and first derivative of displacement will be equal to the velocity. So here we can write BV. I hope this equation 5.5 is clear to you. We just put the value of velocity, or we just replace the displacement with the velocity in this equation. So now we are implementing this equation on MATLAB by using ODE, ordinary differential equation function. I will let you know about this command later on. So first we will suppose the values of the constant like mass, frictional constant, applied force, and then we have to put the equation. So for finding dV over dt, we take this PV on the right hand side, so it is positive become negative, and m will be divided with FA of t minus BV. So here you can see the same equation written in the coded format. So in the next step, this section is basically a function. We have created a function on MATLAB. The function name we are using is cruisespeed.m, and by creating any function on MATLAB, you have to write function and then define its parameters, like function dv dt equals to cruise speed, which is the relationship between time and velocity. So creating function MATLAB gives you a handy tool to call it again and again. You don't need to write the you don't need to write this whole code again and again, but just you can call this names cruisespeed.m, and it will call this function by itself. So it is a good advantage in MATLAB. Second, we have now we are going to solve this equation. So we have supposed the initial velocity equals to 0, and now we are using ODE function. This is the function name which we have declared in the start. Here you can see cruise underscore speed dot m. So calling this function cruise underscore speed, and this is the time spent from where, because this is because we are solving it with respect to time, so this is the time limit. You can also change this limit if you are going to observe on greater span like 250, 500, or lesser span like 10 or 50. So here we are using time span from 0 to 125, and initial parameter or initial condition is v0, which is equals to 0. Now we are plotting this relationship with respect to time. Grid on basically gives you a graph on the grid, and we have declared the title of our graph. So it will show a graphical format. It will show you the result in the graphical format, and you can see here we are also using dsolve for the same equation. Dsolve, it's another command. I will tell you the difference between, it will also show you the result of this equation, but difference between dsolve and ODE45 we will discuss. But here remember, we are using two functions. One is ODE45 and second one is dsolve to solve this particular equation. Now we will discuss second example, mass spring example. So from the same equation, for the non-linear one, we have equation number